Hello, dear students. In this video, we are going to solve the first term assignment for final year high school classes, where we will begin by doing a graphical reading of the curve of a rational function. Then, we will conduct an analytical study of the function's behavior, and finally, we will study a composite function. Underscore, statement of the exercise. The plane is equipped with an orthonormal coordinate system made up of the point O, the vector I, and the vector J. Two real constants, called A and B, are given. The curve, called CF, represents graphically the function f, which is defined on the set of real numbers, except for the two values -1 and 1. The function f of x is written as follows: 2 plus a divided by x plus 1 plus b divided by x minus 1. The line called t is the tangent to the curve CF at the point A, which has coordinates -2 and 0. First part, graphical reading. 1. Determine the limits of the function f at the edges of its domain of definition. 2. Calculate the value of f at -2, and the value of f at 0, and the value of f prime at -2. 3. Study the sign of the function f of x, as well as the sign of its derivative, called f prime of x. 4. Find the equation of the tangent line t. 5. Construct the variation table of the function f. 6. Show that f of x can be written as 2 times x plus 2, all divided by x squared minus 1. 7. Depending on the value of the real constant m, discuss the sign of the function and the solutions of the equation f of x equals -m. Second part, analytical study. 1. Find the derivative of the function f. 2. Study the variation of the function f. Third part, study of a composite function. 1. Define the function g of x as the function f applied to the opposite of the absolute value of x. This function is defined on the set of real numbers excluding -1 and 1. Determine this function. 2. Show that the function g is both even and injective. 3. Rewrite the function g of x without using the absolute value symbol. 4. Explain how to construct the representative curve of the function g, called CG, from the curve of f. Definition of the function and its domain. The function referred to as f is defined across the entire set of real numbers, except for two forbidden values. The first forbidden value is equal to -1, and the second is equal to +1. These exclusions arise because at these particular points, the expressions within the function would lead to a division by 0, which is considered mathematically invalid. This type of function is known as a rational function. The structure of the function f consists of 3 distinct components: a constant value equal to 2, a first fractional term whose denominator is x plus 1, a second fractional term whose denominator is x minus 1. Reminder: behavior at the extremes. When examining the behavior of a function as the variable grows extremely large or extremely small, this is known as studying its limit at infinity. In such cases, both fractional increasingly small, since they are divided by values that grow significantly in magnitude. the overall value of the function tends to approach the constant value, which is 2. This pattern is represented graphically by a horizontal line that the curve of the function approaches but never actually touches. This line is known as a horizontal asymptote, and it is observed when moving far to the left or right on the graph. Behavior at the forbidden values when the variable approaches the forbidden value that corresponds to -1. Whether from the left side or the right side, one of the terms in the function grows extremely large in absolute magnitude. This causes the function to move toward an extremely negative value. In such cases, we say that the function diverges toward -infinity. In a similar way, when the variable gets close to the forbidden value equal to +1 from either direction, the function grows without bound in the direction. This indicates that the function diverges toward +infinity. Such behavior suggests the presence of vertical boundary lines at the exact locations of the forbidden values. These lines are known as vertical asymptotes, and they mark where the function exhibits extreme behavior. Before we move forward with the video, don't forget to subscribe, give it a thumbs up, share it with others, and leave your thoughts in the comment section. Your support helps us grow and keep learning together. Numerical evaluations. First evaluation. When the function named f is assessed at the value equal to 0, it produces a result of 0. Second evaluation. When the same function f is assessed at the value equal to -2, it again gives a result of 0. Calculating the slope of a tangent line, we now aim to determine the rate at which the function f changes at the point where the horizontal coordinate is equal to -2. To do this, we use a graphical method known as the rate of change, which essentially means finding the slope between two specific points. Here are the coordinates involved in this calculation. The first point has a horizontal value equal to -2 and a vertical value equal to 0. The second point has a horizontal value equal to 0 and a vertical value equal to -3. To find the slope, we subtract the vertical value of the first point from the vertical value of the second point, specifically -3 minus 0. Then we subtract the horizontal value of the first point from the horizontal value of the second point, which is 0 minus -2. This process amounts to dividing the number -3 by the number 2, which gives a slope equal to -1.5. Data and interpretation of the sine table. The table consists of 3 main rows, each offering a distinct perspective on how the function behaves across its domain. 1. First row, variable values. This row presents the possible values of the variable commonly referred to as x. These values are organized according to different intervals or key points. From left to right, we have the following entries: negative infinity, -2, -1, 0, +1, positive infinity. Second row, behavior of the function's rate of change. This row describes the trend of the function's rate of change, often called its derivative. In this case, we observe that the rate of change is consistently negative across all intervals listed. This implies that the curve representing the function is decreasing throughout. In other words, the function is steadily declining without any reversal. Behavior of the function itself. This final row illustrates how the function f behaves. It is positive in 3 regions, from negative infinity to -2, from -1 to 0, and from +1 to positive infinity. It becomes 0 at 2 specific points, -2 and +1. It takes negative values in 2 regions, between -2 and -1, and between 0 and +1. Before we continue the video, make sure to subscribe, give it a like, share it with your friends, and leave a comment below. Your support helps us keep creating and keeps the conversation going. Question 4. Finding the equation of the tangent line. 2 specific points are provided. The first has a horizontal coordinate equal to -2 and a vertical coordinate equal to 0. The second has a horizontal coordinate equal to 0 and a vertical coordinate equal to -3. Both points lie on the straight line referred to as tangent t. To determine the equation of a straight line that passes through 2 points, we follow 3 steps. Step 1. Calculate the slope of the line. The slope is found by dividing the difference between the vertical values, which in this case means -3 minus 0, giving -3, by the difference between the horizontal values, here 0 minus -2, which becomes 2. The final result is a slope equal to -1.5. Step 2. Use the standard form of a line equation. We begin with the expression where y is equal to the slope multiplied by x plus a constant. By inserting the slope value of -1.5, we form an equation stating that the y equals -1.5 times x plus b. Step 3. Find the constant term. We substitute one of the points into the equation to solve for the constant. Using the point with horizontal value to -2 and vertical value equal to 0, we insert those into the equation and solve. This yields a constant equal to -3. Conclusion. The final equation for the tangent line becomes y equals -1.5 multiplied by x minus 3. Alternatively, this equation can be rewritten in implicit form. That is, using a format where both variables are placed together on one side, and would read 2 times y plus 3 times x plus 6 equals 0. Question 5. representing the variation table. This table includes 3 distinct rows that describe how the function evolves across different intervals. 1. First row, values of the variable. The variable progresses from left to right across the following intervals: -∞, -2, -1, 0, +1, +∞. 2. Second row, behavior of the function's rate of change. Throughout all intervals shown, the rate of change of the function remains strictly negative. This tells us that the graph is always sloping downward. In simpler terms, the function keeps decreasing across its entire valid domain. Third row, values of the function itself. Here's how the function behaves as the variable moves through the listed values. It begins with a value equal to 2. As the variable approaches -1, the function sharply decreases toward -∞. Just beyond -1, the function rapidly increases toward +∞. As the variable nears +1, the function again drops toward -∞. Past the value of +1, the function rises to +∞ once more, then gradually descends back toward the value of 2. These abrupt changes reflect the presence of vertical boundary lines, called vertical asymptotes, located at both -1 and +1. The function is not defined at these 2 values, which explains the extreme variations near. Question 6. Goal of the question. The objective here is to demonstrate that the function referred to as f can be rewritten using a new expression. This alternative form involves the following structure: twice the x multiplied by the sum of x and 2, all divided by the difference between the square of x and 1. In other words, the goal is to prove that this newly proposed expression is equivalent to the original one. Starting point of the exercise. We begin with the known original expression of the function named f. It is defined as 2 added to a fraction whose numerator is labeled a and whose denominator is x increased by 1, plus another fraction whose numerator is labeled b and whose denominator is x minus 1. 2 key pieces of information are also provided. When x is equal to 0, the function produces a value of 0. When x equal to -2, the function again results in 0. Step 1. Solving the system of equations. We begin by substituting 2 given values into the expression that defines the function. For x equal, we obtain the result stating that 0 is equal to 2 plus a divided by 1 minus b divided by 1. When simplified, this leads to the first equation. The value a minus the value b equals -2. For x equal to -2, we obtain the result stating that 0 is equal to 2 minus the value a minus the value b divided by 3. This gives us the second equation. 3 times the value a plus the value b equals 6. To solve the system formed by these 2 equations, We proceed as follows. By adding both equations together, we get 4 times the value a equals 4, which means that the value a equals 1. We then substitute this result into the first equation to find the value of b. That gives us the result that b equals 3. Step 2. Simplifying the function. We begin by replacing the values of a and b into the original expression of the function. The new form becomes the function f is equal to 2 plus 1 divided by x increased by 1 plus 3 divided by x decreased by 1. The goal is to transform this into a single. To do that, we place all terms over a common denominator. This shared denominator is obtained by multiplying the expression x increased by 1 with the expression x decreased by 1. Next, we expand each term in the numerator carefully, using well-known algebraic identities. For example, multiplying x increased by 1 and x decreased by 1 gives a result equal to x squared decreased by 1. After expanding and simplifying each component, we arrive at the following structure. The numerator becomes twice x squared plus 4 times x. The denominator becomes x squared decreased by 1. Then we factor the numerator to reveal a more compact form. We take out the common factor, which is twice x. This produces twice x multiplied by the sum of x and 2. The final simplified expression for the function f reads twice x multiplied by the sum of x and 2, all divided by x squared decreased by 1. Question 7. Solving the equation. The value of f equals m. The goal of this question is to solve using a graphical approach. The equation or the function named f takes on a value equal to a constant referred to as m. To find the solutions, we look for the horizontal positions where the curve representing the function f intersects with the horizontal line whose height is equal to m_n. Analysis for different values of m when m equal to 0. The curve intersects the horizontal axis at 2 distinct points, one where x equals 0 and another where x equals -2. When m is a small positive value, the curve intersects the horizontal line corresponding to m at 2 points, both located on the left side of the graph. This means that both solutions for x are strictly negative. When m is a large positive value, strictly greater than 2, the curve intersects the horizontal line associated with m at 2 points again. One is positioned to the left of the origin, while the other is to the right. Therefore, the two solutions for x have opposite signs. One is negative, the other is positive. M is a negative value. Once more, the curve intersects the horizontal line defined by m in 2 places, one on the left and one on the right side of the origin. The two corresponding solutions for x also have opposite signs. One is negative, the other is positive. Two, analytical study. Determine the derivative of the function f. Studied function and derivative calculation. The function named f is defined as follows. F of x equals 2 plus 1 divided by x plus 1 plus 3 divided by x minus 1. Step 1. Calculating the derivative. The derivative is computed term by term. The derivative of the constant 2 is 0. The derivative of 1 divided by x increased by 1 gives negative 1 divided by the square of x increased by 1. The derivative of 3 divided by x decreased by 1 gives negative 3 divided by the square of x decreased by 1. Combining both results, the derivative of f becomes negative 1 divided by the square of x increased by 1 minus 3 divided by the square of x decreased by 1. Step 2. Common denominator. Combine both terms into a single fraction. We use a common denominator. The square of x increased by 1 multiplied by the square of x decreased by 1. The numerator is expressed as follows. Negative of the square of the expression x decreased by 1 minus 3 times the square of the expression x increased by 1. Step 3. Expanding and simplifying. The square of the expression x decreased by 1 gives x squared minus twice x plus 1. The square of the expression x increased by 1 gives x squared plus twice x plus 1. Multiplying the second result by 3 gives 3 times x squared plus 6 times x plus 3. Now we compute the complete numerator. We subtract the result from 3 times the square of x increased by 1 from the result of the square of x decreased by 1. This gives negative 4 times x squared minus 4 times x minus 4. Final expression of the derivative. The derivative of f can now be written as negative 4 multiplied by the sum of x squared plus x plus 1, all divided by the square of x increased by 1 times the square of x decreased by 1. Graphical interpretation. Sign of the derivative. To understand whether the function f is increasing or decreasing, we must examine the sign of its derivative. We consider the numerator, negative 4 multiplied by the sum of x squared plus x plus 1. To determine its sign, we the discriminant of the expression x squared plus x plus 1. That value is found by squaring the coefficient of x and subtracting 4 times the leading coefficient times the constant term. This gives a result equal to -3. Because the discriminant is negative, the expression x squared plus x plus 1 is always strictly positive for any real number. Since the front factor is -4, the complete numerator is always strictly negative. The denominator is the product of two squares, which is always positive, except at x equal to -1 and x equal to +1, where the function is not defined. Educational conclusion: the derivative is strictly negative throughout the domain of definition of the function f. This means that the function is strictly decreasing wherever it is defined. Before we continue the video, make sure to subscribe, give it a like, share it with your friends, and leave a comment below. Your support helps us keep creating and keeps the conversation going. Two, study the variations of the function f. Studied function. The function referred to as f belongs to the family of rational functions. It includes two exclusions. It is not defined when the variable x is equal to -1 or +1. This is because such values would cause a division by 0 within the expressions located in the denominator. Derivative expression. The derivative of the function f, commonly referred to as f prime, is presented in a fractional form. It can be expressed as follows: f prime of x is equal to -4 multiplied by the sum of x squared plus x plus 1, all of which is divided by the product of the square of the expression x plus 1 and the square of the expression x minus 1. Graphical analysis based on the variation table. The presented table is structured in 3 essential rows that help examine the behavior of the function across different intervals. 1. First row, values of x. We analyze the function across the following 4 intervals: from -∞ to -1, from -1 to 1, from 1 to +∞. Second row, derivative of the function f, noted as f prime. Throughout all intervals mentioned, the derivative is strictly negative. This indicates that the function f is strictly decreasing wherever it is defined. Reminder: a negative derivative implies that the curve is sloping downward, which means the function is continuously getting smaller. Third row, behavior of the function f itself. The observed pattern is as follows. As x moves toward -∞, the function begins near the value 2. As x approaches -1, the function drops steeply toward -∞. Just after the discontinuity at -1, the function restarts abruptly from plus infinity and begins descending again, eventually approaching minus infinity near the value 1. Immediately after 1, the function starts once more from plus infinity and gradually decreases toward the value 2 as x tends toward plus infinity. Discontinuities at minus 1 and 1. The function is undefined at these values. This leads to vertical asymptotes, straight boundary lines where the graph either shoots upward or plunges downward. Horizontal asymptote. As x becomes extremely large or extremely small, the function gets closer and closer to the value 2 without ever touching it. This indicates a horizontal asymptote at height 2. Defined function. A new function, referred to as g, is introduced. It is defined as follows. The value of the function g of x is equal to the value of the function f of minus the absolute value of x. In other words, the function g is constructed from the function f by applying an absolute value transformation followed by a sign change. Domain of definition. The function g is defined for all real numbers except for two specific values, -1 and +1. These two values would result in a zero denominator within the function f, which is mathematically forbidden. Therefore, the domain of g includes all real numbers except for -1 and +1. Symmetry study. Even function. Let's recall a standard mathematical definition. A function is called even when, for every value of x in its domain, the value of the function at -x is identical to its value at x. That is, the function is even if g of -x is equal to g of x. Verification for the function g. Let's substitute directly into the expression. The value of g at -x becomes the value of f at minus the absolute value of -x. Now, the absolute value of -x is the same as the absolute value of x. Therefore, f of minus the absolute value of x is simply g of x. Result: the function g satisfies the condition for symmetry. It is an even function. Educational reminder. 1. An even function displays a curve that is symmetric with respect to the vertical axis, often called the y-axis. 2. This means that if a point is located on the graph for a certain value of x, then its horizontal reflection Three. Write g of x without using the absolute value symbol. Objective of the exercise. The goal is to rewrite the function named g without using the absolute value symbol. This reformulation makes it easier to carry out a precise graphical analysis, especially when exploring symmetry and how the function behaves. Breakdown of the function g. The function g is defined as the following composition. The value of g at x corresponds to the value of the function f evaluated at minus the absolute value of x. There are two distinct cases depending on the value of x. Case 1. When x is greater than or equal to 0. The absolute value of x is simply x. Therefore, g of x equals f of minus x. Case 2. When x is strictly less than 0. The absolute value of x becomes minus x. Therefore, g of x equals f of x. Summary. The function g is described by two expressions. For values of x greater than or equal to 0, g of x equals f of minus x. For values of x strictly less than 0, g of x equals f of x. Educational reminder. Why make this distinction? In graphical analysis, it's essential to understand how a function is affected by transformations such as absolute value or sign reversal. When a function includes an absolute value in its structure, this can produce a fold or reflection over the vertical axis. When the input is replaced with its opposite, the result is known as axial symmetry. The graph is flipped horizontally. This symbol-free formulation allows us to visually study the function's behavior across both halves of the graph. More Four. Explain how to graph the curve CG starting from the curve CF. Purpose of the graphical study. The goal is to draw the representative curve of the function called g, which is defined from another function f using a symmetrical transformation. This function g is described as even, meaning it exhibits axial symmetry with respect to the vertical axis, known as the y-axis. Complete definition of the function g. The function g is defined for every value of x according to the following rule. If x is greater than or equal to 0, then g of x equals f of minus x. If x is strictly less than 0, then g of x equals f of x. In other words, the function g takes the values of f to the left of the vertical axis and reflects them to the right while preserving domain exclusions inherited from the function f. Graphical method to draw the curve of g. To construct the curve representing g, follow these steps. 1 is the left portion of the curve of f. Begin by examining the curve of f for values of x strictly less than 0. 2. Apply a horizontal reflection. Reflect that portion across the vertical axis. This means replacing each value of x with its opposite. 3. Draw the right portion of the curve of g. Use the reflected section to sketch the curve on the right side of the graph, corresponding to values of x greater than or equal to 0. 4. Respect domain exclusions. If f is undefined for specific values, such as -1 or +1, then g will also exhibit discontinuities at those same locations. Pedagogical notes about even functions. An even function is defined by the property for every value of x, g of -x equals g of x. Graphical consequence. The representative curve is symmetric with respect to the vertical axis. Application in this case. Since g of x is based on f of x for values of x greater than or equal to 0, the right side of the curve of g is a mirror reflection of the left side of the curve of f. Graphical conclusion. The function g is even, constructed by combining the direct and mirrored values of the function f. It displays vertical symmetry. Its curve is drawn by keeping the left portion of f and reflecting it to the right. Before we continue the video, make sure to subscribe, give it a like, share it with your friends, and leave a comment below. Your support. Dear students, thank you for watching all the way to the end of this video. Until next time, I wish you farewell.